Okay. So we're going to start today's class just by, if we just review quickly what we did on the last module or last lecture. One of the main points that we tried to make, we started off the module by saying that, okay, individual silicon has a certain discrete set of energy levels that we see here on the left, and crystalline silicon has a different set of energy levels as we see here on the right. This is the band structure that we saw. The main difference was you have discrete energy states on the left, and on the right, those energy states, they cluster into bands, what we call the conduction band and the valence band. And this is a new slide that it's on the new version of the notes that I uploaded yesterday. These are what the actual orbitals look like. So this is a dot diagram, a schematic of like a single silicon atom, and below it we have silicon atom that's bonded to 4 silicon atoms around it. The orbitals for a single silicon atom, these are what those orbitals look like. This is what the s orbital looks like. I mentioned that the p orbitals are mutually perpendicular to one another. There's one dumbbell that goes along the x-axis, there's another dumbbell along the y-axis, another dumbbell along the z-axis. So you imagine these 3 dumbbells together, these are where the states where the electrons are. Imagine this is the 3s over here. This is the 3p, 3p, 3p. So there's 6 possible energy states here, 2 in each of the suborbitals, and then another 2 in here. So in a single silicon atom, there's 4 of those states are filled. Okay, 4 electrons are occupying 6 possible energy states. This orbital is completely full, and then 2 of these p orbitals are also are occupied by a single electron. In crystalline silicon, so what you see down here, these are what the orbitals look like. Instead of having the s and the 3p, you have 4 sp3 hybrid orbitals. Okay, they're called hybrid orbitals. They just have a different shape than these the standard orbitals up here. Okay, you can see that they actually look like lopsided dumbbells, where one of the lobes on is much larger than the lobe on the opposite side. Okay, and these large lobes here are what are forming the covalent bonds with the neighboring silicon atoms. Okay, so this is what it looks like in 3 dimensions. Just so you know that these orbitals actually have a physical shape that we like to think of. All right, we talked about this, so we're going to jump ahead here. We talked about the mechanism of electric current, electrons jumping from energy state to energy state. Then we ended off the discussion talking about intrinsic versus extrinsic semiconductors. All right, couple questions for review. What are the 2 types of carriers? Yes? Electrons and holes. Which one moves faster, the electron or the hole? Electrons move faster. Electrons move faster than holes. Okay, electrons are the negative charge carrier, holes are the positive charge carrier. If we want to create a semiconductor with a lot of electrons, what type of dopant should we use? N-type dopant, which is which part of the periodic table? Column 5. Right. If we want to create a semiconductor with a p-type characteristic, meaning lots of holes, then we will dope with a column 3 element like boron, and that creates a p-type semiconductor. All right, we talked about the equilibrium carrier concentrations. By looking at this graph, can you guess which material has the larger band gap? Of these 3 materials, which one has the largest band gap and why? I'm sorry? So let's remind ourselves what this graph is showing first of all. This graph is showing the intrinsic carrier concentration at room temperature. Well, not at room temperature would be this vertical line here, but it's showing the intrinsic carrier concentration versus temperature. Okay, and what we notice is that germanium has the highest intrinsic carrier concentration at all temperatures. Then silicon is down here, and then gallium arsenide is always at the gallium arsenide has the least carrier concentration. So how is this related to band gap? Which one has the largest band gap? Gallium arsenide, that's correct. Why does gallium arsenide have the largest band gap?
Low mobile concentration.
Low carrier concentration. Yes. Okay, we can explain that by the energy band diagram. Remember that this is what the energy band diagram looks like for silicon. The larger the band gap is, the more energy is required to for an electron to go from the valence band to the conduction band. Right? So if you have a large band gap, then you can expect to have a small carrier concentration, low carrier concentration. Let's remind ourselves what causes carrier concentration. All right? A semiconductor, if you have a semiconductor at absolute zero, at 0 Kelvin, it will not be conductive. The valence band will be completely full, the conduction band will be completely empty. If, however, you have enough temperature, if you're at room temperature, a few of these electrons are going to go up into the conduction band. That creates electrons in the conduction band, empty states in the valence band. Okay? So a material that has a large band gap like this, it's going to take more energy for an electron to get into the conduction band. All right? So if we compare two semiconductors with different band gaps, the semiconductor with the largest band gap is going to have the lowest carrier concentration. So you can see gallium arsenide has lower carrier concentration here. Right. Another thing to notice about these is that as we go up in temperature, as we move from left to right in this diagram, this is 500 Kelvin, this is 250 Kelvin, as we go up in temperature, the intrinsic carrier concentration goes up for the same reasons I just mentioned. As you increase temperature, more electron hole pairs are being formed as the electrons are getting elevated to the conduction band. We ended up by talking about with doped semiconductors, and I already asked you a few questions on that. So let's just start today's discussion on how to calculate carrier concentrations. Carrier concentrations are important because they determine the ability of a semiconductor to conduct electricity. Today we're going to start getting at how do we determine the conductivity of a semiconductor. Right? And if we were to make a resistor out of silicon, what would the resistance of that silicon be? We're going to talk about semiconductor resistors in this module. Later we'll talk about semiconductor diodes, and after that semiconductor transistors. So when we're talking about resistance, there's two things that determine how conductive a material is, or how resistive a material is. Okay? One of those things is carrier concentrations. If we have more carriers, what do you expect will happen to the ability of the material to conduct electricity? What will happen to the conductivity of the material if we increase the carrier concentration? It should increase, right? The more carriers we have, the more current we expect to have. That's one thing. So there's two things that determine how conductive a material is. One of them is carrier concentration. It's on this slide. There's a second thing. Well, we're going to talk about that later. But that's how fast the charges move through the material. That's something called mobility. We'll get to that later. So right now let's focus on the first part. Carrier concentrations are important because they determine the ability of a semiconductor to conduct electricity. And in semiconductors, we use a statistical approach to calculate carrier concentrations. So to do this, we have to consider what's the likelihood of finding a carrier in each one of the energy states. This is something called the Fermi-Dirac distribution. And then we have to consider how many available states there are. So, okay. Let's see. There we go. We have a lot of carriers in a semiconductor material. Okay, if we look at the intrinsic carrier concentration of silicon, it's 1.5 times 10 to the 10 per centimeter cubed. There's a lot of carriers, right? Even in intrinsic silicon, which is not that conductive. When you dope it, it goes up by 5 or 6 orders of magnitude. So in order to figure out the carrier concentrations, we have to figure out how many, we have to use a statistical approach. So carrier concentration is, let's write this down. So carrier concentration. What is the definition of carrier concentration? Density of charge carriers. We say that, well, we say the number of carriers. Well, let's take two specific examples. Number of electrons per centimeter cubed, or the number of holes per centimeter cubed. Now, I'm going to give you an analogy to how we calculate carrier concentration. So imagine that we have a parking lot. Parking lot analogy. So we have, let's say you have 100 spaces in Costco parking lot, and we say there is a 4% probability that a spot is full. What is the expected number of cars in the lot? Yes. Does this make sense to everyone? If we have 100 spaces in a Costco parking lot and there's a 4% probability that each spot is full, on average we would have four cars in the parking lot. Right? Does this make sense to everyone? I see nodding heads. Yeah. 100 times 0.04, 4 cars in the lot. Okay, the reason I'm bringing up this analogy is because this is the same thing that we use to describe carrier concentrations. This first thing here, or the second thing here, sorry, we'll start off with that. Density of states is saying how many possible states do we have for an electron to be in? How many of those orbital states do we have that an electron can possibly be in? And how many of those states do we have per centimeter cubed of material? You can think about that as a number of parking spots. The second part is the likelihood that the energy state is full. It's a probability. Okay, so what's the units of probability? For a probability, what's the unit? There's no units, right? Yeah. So this is a probability, the likelihood of finding a carrier in each one of the energy states. That's a number between 0 and 1. It's a probability. If you multiply these two together, then you will get the number of electrons per centimeter cubed. So let me write that down. Similarly, with carrier concentrations, density, let's write this down, number of carriers per centimeter cubed, let's just say electrons, number of electrons per centimeter cubed equals the number of states per centimeter cubed multiplied by the probability that the state is full, or that the state is occupied, let's say. Okay, so this part here is the density of states. And this part here is the Fermi-Dirac function. Okay, so we're going to go into each one of these. We're going to go to each one of these in turn. By the way, so this is the probability of finding an electron. This is the probability of finding that the state is occupied by an electron. That's the probability of finding an electron. How is the probability of finding a hole related to the probability of finding an electron? I think I heard it. It's not the same. It's 1 minus, right? Right. A state is either filled with an electron or it's empty, right? If it's empty, then it's a hole. If it's full, if it has an electron, then it's full. So if the probability of finding an electron is 30%, then the probability of finding a hole is 70%. All right. So moving on to the next slide then. This is the Fermi-Dirac equation. The Fermi-Dirac equation tells us that the probability that an available energy state is occupied by an electron is determined by something called the Fermi level. Okay. Qualitatively, this is the rule of thumb that you should remember. Above the Fermi level, we are not likely to find an electron. Below the Fermi level, we are likely to find the electron. And the way this can make sense to you is think back to when we were talking about the Pauli exclusion principle. Part of that we were saying that electrons like to occupy the lowest energy state, right? Things in nature like to occupy the lowest energy state. So if you were to draw a diagram with a whole bunch of energy states, the electrons would first occupy all the low energy states, and all the higher energy states would remain empty, right? So there's sort of like the line between like where you have a lot of full states and a lot of empty states. That's the Fermi level. So let me just draw that schematically. Let's say we have a whole bunch of energy states here. Right? If we were going to fill up electrons first fill up the lowest energy states first. The more electrons you have, they start filling in the lower energy states first. And then the high energy states, these remain empty. And a lot of these will become full. Depending on how many electrons you have, the electrons always occupy the lowest energy states first. So this sort of dividing line between the full states and the empty states, this is what's called the Fermi level. We call this EF. Fermi level. Okay, so this is denoted by, well, I described to you what the Fermi level is. Now, this function describes the probability of finding an electron at a certain energy state. Notice that this is the energy on the x-axis. This is the probability of finding an electron at that energy state on the y-axis. The probability that the state is full, okay, it's 1 here, meaning below the Fermi level, the probability of finding an electron is nearly 100%. This is the Fermi level here. Once we go past the Fermi level, you notice that the probability drops down to 0. So there's a high probability of that that the state is empty. Now, just to relate that back to what we've been looking at earlier, if we look at these diagrams here, you notice how these energy states were filled and these ones are empty? Okay, we didn't get into all the details of why that was, but think about this. Electrons always like to occupy the lowest energy states first. So if there's a whole bunch of energy states down here, they're going to fill these guys up first, and the ones at the higher energy states, these ones are going to remain empty. All right, so in this case, the Fermi level would be somewhere in the middle here. The dividing line between the filled states and the empty states, that's where the Fermi level is. All right. Now, the Fermi function also shows another important thing, is that it's not black and white, meaning it's not a completely sharp drop-off. A completely sharp drop-off, what I'm trying to say there is that, below the Fermi level, all the states are full. Above the Fermi level, all the states are empty. Okay, that's not the case. Okay, that only happens if you're at 0 Kelvin. Notice that this function, if you're at 0 Kelvin, there's a sharp drop-off like this. Okay, at 0 Kelvin, you will have this situation where below the Fermi level, completely full, above the Fermi level, completely empty. But we don't do things at 0 Kelvin normally, unless you're a physicist. At room temperature, the Fermi function is more a gradual drop-off rather than a sharp cutoff. Okay, so there's sort of a gray zone where the probability is not 100%, and it's also not 0%. So this zone in the middle around the Fermi level is a non-zero probability of finding electrons and holes. So a lot of interesting stuff happens where the Fermi level happens to be. Remember we talked about this earlier. We said if all the states in a band are full, there's no room for the electrons to move, so there's no conduction. If a band is completely empty, then there's a lot of space for charges to move, but there are no charges. So again, the band is not conductive. Right. When a band is partially filled, meaning if the Fermi level is close to one of the bands, you end up getting a situation where there are both electrons and holes, both of them. Okay, we'll talk about that more in a second if that seems confusing right now. Focus on the Fermi function at this point. At 0 Kelvin, the Fermi function looks like a straight drop-off like this. At higher temperatures, it's a more gradual curve between a probability of 1 and a probability of 0. This is what it looks like graphically. On the left here, you have a mathematical description of it. Okay, this is not exactly a sigmoidal function, but it looks like a sigmoidal function. It can be approximated by this exponential formula. This can actually be rigorously derived using Fermi-Dirac statistics. We're not going to go into the details of that in this class, but just know that it can be derived from a fundamental principle. The probability of finding an electron, P of E, is equal to the Fermi function. F of E is equal to the probability of finding an electron at the energy state. It's called F of E because we put the input that we put into the function is an energy state. So we'll pick some energy state in the energy band diagram. We'll find what the energy is. And then the Fermi function can calculate what the probability is from there. Now, we always have the energy in terms of, we represent the energy in relation to the Fermi level. Okay, so notice that this function here, it says E minus EF. If you were to pick an energy here, then E minus EF would be just this distance here between the energy that you're looking at and the Fermi function. Okay, this will make sense when you actually do a problem. These problems are not too difficult using the Fermi-Dirac function. So at higher energy states, the probability drops down to 0. At lower energy, below the Fermi level, the probability shoots up to 100. And you can see that in this equation, as this exponential becomes large, then this whole fraction is going to go to 0. At low values, when this exponential function goes to 0, at low values of E, then this part cancels out, and you're left with 1 over 1, so that's a probability of 1. As I mentioned before, the probability of finding a hole is 1 minus the probability of finding an electron. The probability of finding an electron is 30%, then the probability of finding a hole is 70%. because the state can either be full with an electron or it could be empty. If it's full, it means it's an electron. If it's empty, that means it's a hole. K is a Boltzmann constant, 1.38 times 10 to the negative 23 joules per Kelvin if you're in MKS units. For the purposes of this class, you will be using this version a little bit more often. 8.63 times 10 to the negative 5 electron volts per Kelvin. Okay. Remember that 1 joule is 1.6 times 10 to the negative, 1 electron volt is 1.6 times 10 to the negative 19 joules. They're both units of energy. Right, and the EF here is the Fermi level. Questions? Okay. One thing that students often get confused about in this class is they say, well, what happens at 0 Kelvin? At 0 Kelvin, like mathematically, you have a 0 in the denominator here, right? Mathematically, a 0 in the denominator is undefined. So if I ask you to figure out the Fermi-Dirac distributions of the probabilities at 0 Kelvin, you can't use this mathematical equation. You just have to use the rule of thumb that we mentioned. At 0 Kelvin, the Fermi function looks exactly like this. So above the Fermi level, you have 100% probability. Below the Fermi level, you have 0% probability. I'm sorry, I said it the opposite. Below the Fermi level, 100% probability. Above the Fermi level, 0% probability. Okay. 0 Kelvin, don't bother trying to use the equation. Questions?
The Fermi level is based on the physical properties of the material?
Yes, the Fermi level is based on the type of material that you have. Also, it's very dependent on the doping.
So it'd be given, basically, or you have to derive, or will we be given something else and have to find it?
Yeah, so the question is will the Fermi level be given to you, or will you have to figure out the Fermi level yourself? The answer is that you'll have both types of problems. It turns out there's a relationship between Fermi level and doping. The more you dope a semiconductor material, the higher up the Fermi level goes. And the more I'm sorry, let me rephrase that. The more N-type a semiconductor is, the higher the Fermi level is. The more P-type a semiconductor is, the lower the Fermi level is. Okay, so in some cases, I will give you the doping and you'll figure out the Fermi level. In other cases, I'll give you the Fermi level and you have to figure out the doping. If this sounds confusing right now, it'll make sense when we do some of these examples. All right, this slide is showing some more details on visualizing the Fermi distribution and the Fermi level. Basically, visualizing the electron and hole distribution based on the Fermi level. All right, the rule of thumb is this. Okay, this is something you should memorize. If you don't memorize it now, you will definitely know it by probably just in a few weeks, because this is just a basic rule of thumb that you have to know. The closer the Fermi level is to the conduction band, or the higher the Fermi level is, the more electrons you'll have in the conduction band. And this is what's referred to as an N-type semiconductor. If you dope the semiconductor N-type with a column 5 dopant, the Fermi level will move up. Okay. The opposite is also true. The closer EF is to EV, meaning the lower the Fermi level is, the more P-type a semiconductor is. So if you dope it with a column 3 element, you'll basically be moving the Fermi level down. And then in an intrinsic semiconductor, the Fermi level is halfway between EC and EV. So we've been drawing our band diagrams. Last time we drew a band diagram, we said there's a simplification. Our simplified band diagram will look like this. We have EC and EV, and then we have the band gap in between them. Does anyone remember what the band gap of silicon is? Just for trivia.
1.4.
1.12 electron volts. .12 eV. All right, so this was our simplified diagram from before. Now what we're doing is we're going to add in EF to the diagram. So for an intrinsic semiconductor, EF will be right in the middle between EC and EV. So 0.56 electron volts here, 0.56 electron volts here. If it's an N-type semiconductor, EF will be higher up. If it's a P-type semiconductor, EF will be further down. So let's try to make sense of these rules of thumb that we just mentioned. Let's first look at the intrinsic semiconductors. Let's zoom in here. So in the intrinsic case, the Fermi level is right in the middle, in between EC and EV. Now, one of the things that I mentioned was that the Fermi function is not a sharp drop-off. It's a gradual drop-off from 100% probability to a 0% probability. So when EC and EV, there's not a large distance between EC and EF. There's not a large distance between EF and EV. What that means is that at EC, we are going to have a small but non-zero probability that the state is filled. Let me state that again. The Fermi function goes from 1 to 0. So what we've done here is we've turned the Fermi function 90 degrees. We've turned it on its side so you can just visualize the Fermi function alongside the energy band diagram. The Fermi function EF. Now I should have mentioned this on the last slide. The definition of the Fermi level is where the probability is 50%. Okay, remember I was saying this is the EF is sort of the dividing line between high probability and low probability. So the specific number that we use, EF, at the Fermi level, the probability of finding an electron is 50%. All right, so you can see at the Fermi level here, the Fermi function is at 50%, 1/2. You can see here, this is 1, 1/2, 0. By the time we get to EC, you can see that the Fermi function has dropped off to almost to 0. But if you look at this zoom-in section, you'll notice that the Fermi function is not completely 0. Right? There might be a 0.001% probability that there's an electron there. Actually, the probabilities are much smaller than that even. But I'm just telling you, just as an idea here. All right, non-zero probability means that there will be some electrons there. There won't be that many, but there will be some. Now, does anyone remember what happens if you have electrons in the conduction band? You have electrons and you have a lot of empty states. Can the material conduct electricity?
Yes.
That's correct. How about if you have, the opposite is also true. You actually end up having a few holes in the valence band. So that can also conduct electricity, right? So let's talk about this whole issue here. If we zoom in on this part of the diagram, we can see that the probability is close to 1, but it's not completely 1. It might be 99.9999% probability that the state is full. So most of the states will be full, but there might be a few empty states, and that's what the holes are here. Right? So an intrinsic semiconductor at room temperature, this is what we were getting at earlier, an intrinsic semiconductor at room temperature has some of these electron hole pairs, and it can conduct electricity. It's just not a very good conductor. So the same concept we're showing again, except we're showing it with the Fermi function now. All right, now moving on here. Any questions about the intrinsic diagram? So let's move on to here. This is the N-type. Oops. Bear with me here. There we go. Misbehaving. All right, so for an N-type semiconductor, the Fermi level is closer to the conduction band. All right, by moving the Fermi level up, let's look at what happened to the Fermi function. If we compare these two, in the case of the intrinsic semiconductor, the Fermi function had a very small value. Okay, that's represented schematically here. And for the n-type semiconductor, the Fermi function has a larger value here, meaning there's a higher probability of finding an electron. The closer the EF is to EC, the higher the probability of finding an electron at EC. This is where the electrons are. Higher probability means you're going to end up with more electrons here. So if there's more electrons, then this conduction band becomes more conductive. This is the example of a doped semiconductor, an n-type semiconductor. So what does this do to the number of holes? If we move the Fermi level up, let me ask this as a question to the class. If we move the Fermi level up, yes, we created more electrons. What happened to the number of holes? Do we increase or decrease?
Decrease.
We decrease the number of holes here. By moving the Fermi function up higher, now there's a larger distance between EF and EV. That means this probability is even closer to 100% than before. So we get fewer holes. Okay. So what we're seeing from this is that there's an inverse relationship between the number of holes and the number of electrons. In the case of the intrinsic silicon, there's an equal number of electrons and holes. Okay, remember we were saying that electrons and holes are created in pairs? So the number of electrons and holes are equal to each other. In the n-type semiconductor, we've moved the Fermi level up. Now we have more electrons and fewer holes. In the case of a p-type semiconductor, it's the opposite. We have fewer electrons and many holes. The Fermi level is closer to the valence band. Okay. What would happen if we were to move the Fermi level above the conduction band? Let's say we move the Fermi level way up here, where I'm showing here.
There would be conduction.
There would be conduction, yes, that's correct. Why would there be conduction?
But you still have more electrons than
Yeah, you'd have a lot of electrons up here. If we move the Fermi level up here, we are increasing the probability that some of these states are filled with electrons. That will create more, the conduction band will become even more conductive. All right, good. So just to complete this, this is the example of the p-type semiconductor. The Fermi level is close to the valence band. If we zoom in here, we can see that the probability here of finding an electron is almost 100%, but not quite 100%. That means there's some probability that the state is empty. So there ends up being holes in the valence band and fewer electrons in the conduction band. So that's a little bit about the Fermi level. Now, just as an example here, which of these acts as a metal? Which ones acts as an insulator? Which ones act as a semiconductor? Just by looking at these diagrams here. And in answering these questions, what I want you to think about is, what I want you to answer rather, is that which bands are conductive and which ones are not conductive. In order to be a metal, in order to be a conductor, you have to have a band that's very, very conductive. In order to be an insulator, you have to, all three bands have to be non-conductive. And in the case of a semiconductor, you'll have a situation where some of the bands are partially conductive. So if we were to look at this diagram, and you can take a minute to think about it, which of the ones would be metal, which ones would be an insulator, which one would be a semiconductor, and why?
material 2 would be metal and insulator.
I'm sorry, go ahead.
The left one is semiconductor, and the middle one is metal, and the right one is insulator.
Yeah, very good. very good. So let's go through and explain them then. So let's do material 2 first. Okay. Oh no. Let's start with material 1. So material 1 has EF is directly in between two of these bands, between band 2 and band 3. So why do you believe that this is a semiconductor? Remind me your name again.
I'm
Tom.
Tom.
Okay.
I thought it's between the band 2 and band 3. But
Okay. It's between band 2 and band 3.
But compared with the material 3,
Okay.
there's a way big band gap between band 1 and band 2.
Okay.
Who will be a semiconductor, the number 1, and number 3 will be an insulator.
Yes. So material 1 will be a semiconductor, and this will be an insulator. That is correct. So your point is well taken that the Fermi level is in between the two bands. Okay. Let's get into some more specifics now. What does that mean in terms of which bands will conduct electricity? So, yeah, Andrews?
Yeah, I think if it is in between that, then that means that both bands, the conduction band and the valence band, like the conduction band will have electrons,
Mm-hmm.
and then the valence band will have partial holes as well. And because the
That's
gap
right.
is very small, in this case there will be conduction. But if you go to the insulator, you have the same process occurring because the EF is in between, but the only difference is that the gap difference is very high,
Yes.
and therefore the conduction is going to be, there may not be enough conduction. But when you come to the case of the metal, there's an overlap.
Absolutely.
So that's why there will be conduction all the time, because the EF is actually below, it's within the
It's
valence
within the
bond.
band.
Yes.
Exactly. All right, let's go over those points again. In material 1, you notice that EF is in between band 2 and band 3. So as Andrews was saying, what that means is that, at EF, remember that the way that we look at EF, below EF the states are filled, above EF the states are empty. And when EF is close to any one of those states, then those states have a possibility of being partially filled. So in analyzing this problem, what we have to do is we start out with band 1. Okay, band 1 is way below the Fermi level, right? So band 1 is therefore, it's completely full. If it's completely full, it's not going to conduct electricity. Moving up to band 2. Band 2, you can see that the upper part of band 2 is close to the Fermi level. It's below the Fermi level, but close to it. That means that band 2 is going to be mostly full, but some of these states near the top of band 2 might be empty. Right? So we don't have to call this a valence band or conduction band. That's not important, right? But the point here is that band 2 can be partially filled. So this band can conduct electricity somewhat. In band 3, is band 3, how do we describe band 3? Yes? Mostly empty. Yeah, mostly empty, but notice that the states here that are close to EF, those ones will be some small probability that the states are full. All right? So band 3 then is also partially filled. Doesn't have that many carriers, so both of these bands can conduct electricity, but just not that well. If we compare this to an insulator, jumping to material 3, again we do the same analysis. Band 1 is quite far below the Fermi level, so this is full. Band 2 is quite far above the Fermi level, so this is empty, and this is empty. So bands 2 and 3 don't conduct electricity. Bands 1, 2, and 3, none of them conduct electricity. Band 1 is full, band 2 and 3 are both empty. So the difference between material 1 and material 3, as Andrews pointed out, was that EF, there's a small gap here between the two bands. The band gap here is small, and in this case the band gap here is large. Right, large band gap materials tend to behave more as insulators. Now if we look at material 2, this is an example of a metal. Again, we do the same process. We look at band 1, we say that band 1 is way below the Fermi level, so this one's full. Band 2, the Fermi level runs right through the middle of it. So right, we're going to have a situation where the band is half full and then half empty. This is like the ideal condition for having, you have a lot of carriers and you also have a lot of empty states. You have the charges and the charges can move around. That's the ideal condition for electricity conduction. So if you ever see a band diagram that looks like this, where the Fermi level is situated within the band, that is a conductive material, very conductive material. How about band 3? It's empty. So band 3 does not conduct electricity. Band 1 does not, but band 2 is responsible for the conduction. So something interesting that happens with the semiconductor, let's say this was, let's go back to the diagram for silicon. I'll just show it up here. All right, so as we move up, as we dope this more n-type, the Fermi level moves up. Right? If we dope it enough, it is possible to actually dope it high enough where the Fermi level actually can go above the conduction band. Right? This is the case where you'd have a semiconductor acting as a metal. Very highly doped semiconductor will become very conductive and it'll act like a metal. That's if the Fermi level, if the Fermi level is above EC. So this is. All right, so now we've covered this first part of the problem. We've talked about the Fermi-Dirac distribution. This is the probability that the state is full. The next thing we'll talk about is the density of states. How many available states are there? So the density of states function tells us the number of available energy states in a semiconductor volume at some energies. The exact formula for NEDE can be found using quantum mechanics. You don't need to know it for the class. However, I want you to qualitatively understand that the density of states is not constant. Now, what do I mean by that? If we go back to an earlier diagram that I showed you, this one. I mentioned that all the energy states are clustered into two bands, the conduction band and the valence band. Now, if we look at this diagram, it really, the way that I've drawn it, it looks like the density of states here is equal, right? You see that there's an equal number of, there's an equal spacing between the lines, right? This is not quite accurate. What actually is true is that there are fewer states at the bottom and there are more states the farther up in energy that you go. All right, if I were to draw it accurately, I'd draw a few lines with more spacing here, and then as we go to higher energies, there'd be less and less spacing between the energies. So this is what we're talking about. When we're talking about density of states, we're talking about the number of states per electron volt. So the density of lines along the y-axis. There are fewer states near the edge of the conduction band. There's more states as we go up. And it turns out that relationship is a square root relationship. Qualitatively understand that the density of states is proportional to the square root of E. All right. Therefore, in a semiconductor, the density of states increases as we go above EC, and it also increases as we go below EV. It should be increases. All right. So at the edge of the conduction band, at the edge of the valence band, there are fewer states, but as we go further down in the valence band, more states. As we go higher to the conduction band, there are more states. And it goes up as a square root function. Now, the energy states, does anyone remember how do we find the energy states? I guess you should know that by now. How do we mathematically find where the energy states are and what energies they're at? What's the equation that we talked about in Module 2? The Schrodinger equation, right? We're not going to solve the Schrodinger equation, which is why you're not seeing any formulas on this slide. The Schrodinger equation tells us what the density of states is. When we solve for them, we'll find, the Schrodinger equation will tell us it'll have certain solutions. Each solution corresponds to an energy state. And we can graph out what those different energy states are. And what they look like, the shape of the orbitals and things like that. The density of states near the conduction and valence band can be approximated with these two formulas. Okay, you're not going to be really using them in this class, but it's useful for you to know. We're just going to be using them to derive a simpler set of formulas which we can use in our calculations and the types of problems that you'll be doing in this class. So, with carrier concentrations, the carrier concentration, this portion here, carrier concentration is also called carrier density. Carrier concentration is equal to the density of states multiplied by the probability that the state is full. The units for density of states is number of states per centimeter cubed. You're multiplying that by a unitless amount. And so the units that you get here is the number of electrons per centimeter cubed. Or if you're talking about holes, the number of holes per centimeter cubed. So as a general rule to calculate, carrier concentration, we multiply the density of available states by the probability that the state is filled. So N0 is equal to the effective density of states multiplied by the Fermi function. So for example, at the conduction band EC, N0 is equal to this effective density of states which we saw on the previous slide. This is the density of states near the conduction band, multiplied by the Fermi function at EC. And we come up with this formula here. This is a formula for the electron concentration. At the valence band EV, we have a similar formula. This is the effective density of states at the valence band, and then we plug in EV into the Fermi function here, and we come to this equation describing the whole concentration. All right, but these forms of the equations are, you can use them, no problem, if you have the values for the density of states NC, and you also have the value of the density of states NV. We won't be using those in this class very much. I'm going to show you a simpler way to do some of these calculations. We'll get to that in a second. Let's just cover some more concepts before we get to that. So the density of states is higher as we move further away from EC and EV. However, the Fermi distribution is lower the farther we move away from the Fermi level. So let's look at an example of that. All right. So this plot is showing here on the left, you see the energy band diagram. You have EC, EV, and you have EF in the middle. So this is an intrinsic semiconductor. The second graph here is showing the density of states. The third graph is showing the Fermi function. And the fourth graph is showing the product of the two. So this is the carrier concentration being shown on this portion of the graph. All right, the density of states I mentioned, it goes up. And at the higher the energy you go, the number of states goes up. That's why you see this function here and this function here. This function is being multiplied by the probability that the state is full, the Fermi function. And the Fermi function looks something like this. So if you take these two functions and you multiply them together, you end up with functions that look something like this. Okay, you get an electron concentration here, and you get a hole concentration here. Remember, the electron concentration is calculated by multiplying the density of states with the Fermi-Dirac distribution directly, and the hole concentration is found by multiplying the density of states with the inverse, or 1 minus the Fermi function. And that gives you the hole concentration here. All right, we showed that mathematically on the previous slide. What we're doing now is we're showing it schematically. I'd like you to have a picture, a graphical idea of what these things look like. So you have a high concentration of electrons just at the edge of the conduction band, and you have a high concentration of holes just at the edge of the valence band. Now the reason why that happens is, remember, the higher up in energy you go, the probability of finding an electron drops to 0 very quickly. So at high energies, you will not find any electrons. The density of states function goes up as a square root of E. So at the edge of the conduction band, there aren't any states, though there is a non-zero probability that the state is filled. When you multiply these two functions together, you see that you have no electron concentration at the edge of the conduction band. The electron concentration goes up a little bit, and then it falls down because, now at this point you're getting to the point where there may be a lot of states, but there's no probability that the state is full. It's coming from the fact that the Fermi-Dirac distribution dropped to 0. And the same thing happens with the holes in the valence band. So when we draw our energy band diagrams, you notice that this is the way we drew them. We drew the electrons at the edge of the conduction band. We drew the holes at the edge of the valence band. This is why we do that. All right, so now moving on for an N-type semiconductor. So for an N-type semiconductor, this is what it looks like. This is the energy band diagram here on the right. So the N-type semiconductor, the Fermi level is close to the conduction band. The Fermi function is shifted upwards compared to the intrinsic energy state. So that's the only thing different between the intrinsic and the N-type. Right, the Fermi function is shifted upwards. Because the Fermi function is shifted upwards, you end up with a higher electron concentration in the conduction band, and you end up with a lower hole concentration in the valence band. So in the intrinsic one, the electron and hole concentration were relatively equal. Now it's skewed. You have a lot of electrons and fewer holes. And if we go to the p-type, the Fermi level close to the valence band, in this case we have a lower electron concentration, a higher hole concentration. All right. So I suggest you go through these. I suggest that you go through some of these things on your own if it's a little bit confusing at first glance. This is something that conceptually you should understand. Let's finish up with this real quick, and we'll talk about behavior of carriers after the break. So with multiple dopants, what happens if we put donors and acceptors? In this example, ND is much greater than NA. So let me ask that to the class then. So let's say we were to first dope the material p-type. So we put boron atoms in there. Then we subsequently dope it n-type. So we start throwing in arsenic atoms in there. What do you think will happen?
They offset each other?
They offset each other. Why would they offset each other?
Well, because it was now naturally in balance, then you increase one concentration and then you just reproportion everything, right?
You are essentially reproportioning everything. Yeah.
The Fermi distribution would be closer to the E sub C, right? Because you're adding more numbers.
Whenever you add more donors, E sub C, the Fermi level moves up towards the conduction band, towards EC. And when you add acceptors, it moves back down. So essentially, in terms of the energy band diagram, you're basically moving the Fermi level one direction, then you're moving it back in the opposite direction. If we think about it more conceptually, you should understand these things not just in terms of the energy band diagram, also in terms of what's physically happening in the material. We had this, let's see. If you remember from class last time, we were drawing this out. Phosphorus has 5 electrons in its outer shell. Boron has 3 electrons in its outer shell. And we showed this example of when a boron atom a boron impurity is implanted into the lattice, meaning like you're doping it p-type, you end up with having an incomplete bond here, right? Because boron has 1 less electron than silicon does. So for every boron atom that you put into the lattice, you get 1 hole. Now, let's say we now doped it with arsenic. So let's say this silicon atom is now replaced with an arsenic atom. What happens if we put an arsenic atom into the lattice? Arsenic is column 5. It creates an extra electron. So let's draw in the extra electron. What do you think the extra electron is going to do when it sees an empty state? It's going to fall right into it, right? So this guy falls right in here. Now you've essentially, you're back to silicon. You don't have like electrons or holes. So using multiple dopants, one dopant can actually offset the other. All right. So if you don't have a one-to-one relationship, in this example, let's say Nd is much greater than Na. You dope with a certain density of acceptors, like 10 to the 14th, let's say, and then you dope with a much higher concentration of donors. What's going to happen? Is it going to be N-type or P-type? It'll be N-type, right. Whatever has a higher doping concentration that's the type the material will become. So this diagram sort of shows what happened here. If you first dope it with acceptors and then you dope it with donors, the Fermi level is still N-type. The ED, recall this is coming from the fact that you've doped with donors, and the EA is coming from the fact that you doped with acceptor atoms. So this is what would happen if you do multiple doping steps. First you dope at P-type, and then you dope at N-type. So are any of you wondering why would you do that to begin with? If you want an N-type material, why would you even bother doping at P-type initially? Why not just make it N-type right from the start? Right. Is anyone wondering that? Hopefully. Okay, good. So for those of you who were thinking about that, this is the reason why. It's more a practical reason. You know, a lot of times when we make, some of you might remember, if this is something we'll talk about later, if you want to make a semiconductor transistor, a MOSFET looks something like this, where you have a P-type substrate, and then you have these N-type regions within the P-type substrate. Okay. The way that you make this is that initially you start off with a P-type substrate like this, and then you implant N-type material into here. So the point I'm trying to make is that the whole thing was initially P-type, but by implanting extra donors just into this region, you can switch it from P-type to N-type. This is how a transistor is made. Yes?
So do they like carve out these canyons, I guess, for the N-type, or is it all mixed in at once?
Yeah. So your question is how do we define which regions become N-type?
Yeah.
That's what we'll talk about in the semiconductor fabrication module, where you guys go to the clean room and we'll have like a lecture on that. How you can use what's called photolithography, to define where these n-type regions are going to go. So an electronics designer would actually do that. They would say, we want our source to be here, we want our drain to be here, this is what the substrate looks like, this is where the gate is going to be. So have any of you heard that term VLSI? VLSI design? We have a VLSI design course here at our department. That's what you do in that class. You take circuit schematics, where you draw your transistors, and people take those circuit diagrams and then they convert that into what it's actually going to look like on the semiconductor. All right, good. So we'll end with this. I think we're going to do the presentations and then we'll do the quiz. So I just want to finish up with this here. When you have multiple dopants, you have to maintain space charge neutrality. For a material to remain electrostatically neutral, this has to hold. P0 plus Nd is equal to N0 plus Na. P0 is the number of holes in the material. This has a positive charge. Nd is the number of donors. This also has a positive charge. Okay, if you recall, Nd is an arsenic. It doesn't like it when I do this. Let me rewrite the formula here. P0 plus Nd is equal to N0 plus Na. When we're talking about Nd, this is the number of ionized donors. So remember, when an arsenic ion, when it loses that electron, the nucleus becomes positively charged. An ionized acceptor atom like boron, right, when that hole leaves, it acquires an effective negative charge. All right, so this is a hole. A hole has an effective positive charge. An electron has an effective negative charge. So this statement here, the space charge neutrality, is basically saying that the number of positive charges in the material has to equal the number of negative charges in the material if the material is going to be electrostatically neutral. And materials are electrostatically neutral. So when you have these problems where you're trying to solve, if I tell you that, okay, I've doped at n-type with this amount, I've doped at p-type with this amount, then if you want to figure out what the hole in electron concentration is, you have to use this formula. This is the thing I mentioned earlier. An n-type material can be made p-type by adding more acceptors. Na is much greater than Nd. And if you want to convert it from p-type to n-type, you just dope with Nd much larger than Na. All right, questions? All right, good. So let's take a short break. Let's just take a 3-minute stretch break. Let's get the presentation ready so that we can do that. And then we will go for, we'll have about 10 more minutes of lecture, and then we'll finish up for today. And we'll have the quiz after that. Okay, so now that so far we've looked at calculating carrier concentrations based on the density of states in the Fermi function. And we've also talked about simplified energy band diagrams of n-type, p-type, intrinsic silicon. We haven't talked about E versus K diagrams. We will see if we get to that by the end of the module. Probably not. In past years, we've just left this portion of it out in favor of including other things in the class. What I'm going to talk about now is the behavior of carriers. How carrier concentration varies with temperature and doping. How carriers move in the presence of electromagnetic fields. So in that, we'll talk about mobility, scattering, and all this other good stuff. Continuing on this discussion from before, we were showing this slide here where we calculated the electron concentration we also calculated the hole concentration. And I mentioned that we have these formulas here based on NC and NV and the Fermi function. There are easier versions of those formulas that we can work with when we do our calculations. So that's what we're going to talk about now. These were the previous formulas we had, just rewritten up here. If we multiply these two together, so we multiply N0 and P0, we will come up with this longer equation here. So you notice we have NC, we have NV, and then we have two exponentials. What happens if you have two exponentials like e to the negative, e to the a multiplied by e to the b? What is that equal to? If you have e to the a and then e to the b, multiply them together, e to the a plus b, right. So that's essentially what we're doing here. We're just taking these two exponents, we're adding them together, and when you add them together, what you notice is that the Fermi part of it, the EF, since it's present on both sides, this drops out. This ends up dropping out. So you end up with just this, EC minus EV divided by KT. Now EC minus EV is a constant, right? This is EC, and this is EV. For silicon, the difference between them is 1.12 electron volts. That's the band gap. That's a constant for a given material. Diamond has 4-something electron volts. Gallium arsenide is 2-point-something electron volts, and germanium is like 0.6. Every different material has a different band gap. So this EC minus EV here is just the band gap. So now we have a formula. N0 times P0 equals NC NV e to the EG over KT. These are all constants. NC is a constant, NV is a constant, EG is a constant. So the product of the electron and hole concentration is always constant in a given material and in a given temperature. Now, I'm describing this to you mathematically. Remember what we were saying earlier. The more holes you have, the fewer electrons you have. And the more electrons you have, the fewer holes you have. We were talking about that earlier in the context of we were showing N-type and P-type materials. So this is telling us that the product of the two is always a constant. So if that's true, then it makes it easy. If you know the electron concentration, you can calculate the hole concentration. If you have the hole concentration, you can calculate the electron concentration. So that's what we're getting at here. This is where we talk about the intrinsic carrier concentration. Now we've defined that earlier. Does anyone remember what intrinsic carrier concentration is? We defined it, I believe, last Thursday.
Number of electrons per cubic centimeter for non-doped.
Exactly. Very good. It's the number of electrons or holes per cubic centimeter in an intrinsic, a non-doped semiconductor. So that's what I'm bringing back from earlier. Ni is equal to Pi. The intrinsic electron concentration is equal to the intrinsic hole concentration. This is for an intrinsic semiconductor. Now if we multiply Ni and Pi together, we get this relation, Nc times Nv, e to the negative Eg over Kt. All right, this is from the last slide. This is for, we're doing this calculation that we've seen here. We're doing this for an intrinsic semiconductor. For an intrinsic semiconductor, the electron concentration is going to be Ni. The hole concentration is going to be Pi. And for silicon at room temperature is 1.5 times 10 to the 10. It's a constant. You multiply these two together. Ni times Pi, they're both equal to each other. They're equal to Ni squared. All right, these Pi is equal to Ni. So you end up with Ni squared on the left-hand side here. And when you take the square root of it, you have an equation for Ni. Square root of Nc Nv e to the Eg over 2Kt. This is a formula for Ni. I gave you guys the value of it, 1.45 times 10 to the 10 per centimeter cubed. That can be calculated by using this formula here. Okay. You won't be using this much in this class because for all practical purposes, the value for Ni is just given to you. Right? Usually we're working with room temperature. But if you need to calculate Ni at a different temperature, you can use this formula to do it. All right, to do that, you'd need to know Nc and Np. So from these relationships, okay, we can come to this conclusion that N times P, N0 times P0 is equal to Ni squared. So note that Ni squared is the same as the product of N0 times P0. This gives us this important relationship that we're using everywhere here. All right, so this Ni squared is equal to Nc times Nv e to the Eg over Kt. We also have this relation up here. Ni times Pi is equal to the same thing. So therefore, Ni times Pi is equal to Ni squared. This was derived for an intrinsic semiconductor, but it's also applicable to an extrinsic one as well. This formula here is very important. Okay, this is one that you're going to be using over and over during the course of this semester. N0 times P0 is equal to Ni squared. Ni, you know, it's defined as 1.5 times 10 to the 10 per centimeter cubed at room temperature. So if you know the electron concentration, you can figure out the hole concentration, and vice versa. I think it's worth it that we do a really quick example of how this formula is useful. So let's say I say the doping. So we have silicon doped N-type. And we say Nd, the number of dopants, is equal to 10 to the 16th per centimeter cubed. Okay? So this means we put in 10 to the 16th arsenic atoms for every centimeter cubed of material. And what we want to do is find N and P. We call it N0 and P0, the electron and hole concentration. What is the electron concentration going to be? And I'll give you a hint. This one is very simple. You don't need to do any calculations at all. Sorry? I think I heard it.
10 to the 16th.
Why is it 10 to the 16th? Exactly. It's equal to Nd, 10 to the 16th. And the reason why is, recall that for every arsenic atom that was put into the lattice, every arsenic atom is donating one electron. It's creating one electron. So there's a one-to-one relationship there. So N0 is equal to Nd, it's equal to 10 to the 16th per centimeter cubed. This is where the Np equals Ni squared becomes very useful. You have this relation N times P equals Ni squared. So if we now want to find the hole concentration, P0 is equal to Ni squared over N0, 1.5 times 10 to the 10 per centimeter cubed divided by N0, which we just calculated as 10 to the 16th. Does anyone have a calculator can help me out here? This is 1.5 times 2.25 times 10 to the 20th minus times 10 to the 20th, yeah, times 10 to the 4th per centimeter cubed. So this is an example of an N-type material. So notice that the electron concentration is 10 to the 16th. The hole concentration is something like 10 to the 4th. You have a lot of electrons, very few holes. All right, so this formula is very useful in just, if you know the electron concentration, you can find the hole concentration and vice versa. All right. We will get into this next time.